In machine learning, the perceptron is an algorithm for supervised classification of an input into one of several possible non-binary outputs. It is a type of linear classifier, that is a classification algorithm that makes its predictions based on a linear predictor function combining a set of weights with the feature vector. The algorithm allows for online learning, in that it processes elements in the training set one at a time. The perceptron algorithm dates back to the late 1950s. Its first implementation, in custom hardware, was one of the first artificial neural networks to be produced. History. See also, History of Artificial Intelligence, AI Winter. The perceptron algorithm was invented in 1957 at the Cornell Aeronautical Laboratory by Frank Rosenblatt, funded by the United States Office of Naval Research. The perceptron was intended to be a machine, rather than a program, and while its first implementation was in software for the IBM 704, it was subsequently implemented in custom-built hardware as the Mark I perceptron. This machine was designed for image recognition. It had an array of 400 photocells, randomly connected to the neurons. Weights were encoded in potentiometers, and weight updates during learning were performed by electric motors. In a 1958 press conference organized by the U.S. Navy, Rosenblatt made statements about the perceptron that caused a heated controversy among the fledgling AI community. Based on Rosenblatt's statements, the New York Times reported the perceptron to be the embryo of an electronic computer that, the Navy expects will be able to walk, talk, see, write, reproduce itself and be conscious of its existence. Although the perceptron initially seemed promising, it was quickly proved that perceptrons could not be trained to recognize many classes of patterns. This led to the field of neural network research stagnating for many years, before it was recognized that a feed-forward neural network with two or more layers had far greater processing power than perceptrons with one layer. Single-layer perceptrons are only capable of learning linearly separable patterns. In 1969 a famous book entitled Perceptrons by Marvin Minsky and Seymour Papert showed that it was impossible for these classes of network to learn an XOR function. It is often believed that they also conjectured that a similar result would hold for a multi-layer perceptron network. However, this is not true, as both Minsky and Papert already knew that multi-layer perceptrons were capable of producing an XOR function. 3 years later Stephen Grossberg published a series of papers introducing networks capable of modeling differential, contrast enhancing and XOR functions, 213 to 257, online, 1. Nevertheless the often miscited Minsky-Papert text caused a significant decline in interest and funding of neural network research. It took 10 more years until neural network research experienced a resurgence in the 1980s. This text was reprinted in 1987 as Perceptrons, Expanded Edition, where some errors in the original text are shown and corrected. The kernel perceptron algorithm was already introduced in 1964 by Zerman al. Margin bounds guarantees were given for the perceptron algorithm in the general non-separable case first by Freund and Shapire, and more recently by Mori and Rostamizadeh, who extend previous results and give new L1 bounds. Definition: in the modern sense, the perceptron is an algorithm for learning a binary classifier, a function that maps its input to an output value. Whereas a vector of real-valued weights, is the dot product, and is the bias, a constant term that does not depend on any input value. The value of is used to classify as either a positive or a negative instance, in the case of a binary classification problem. If is negative, then the weighted combination of inputs must produce a positive value greater than in order to push the classifier neuron over the zero threshold. Spatially, the bias alters the position of the decision boundary. The perceptron learning algorithm does not terminate if the learning set is not linearly separable. If the vectors are not linearly separable, learning will never reach a point where all vectors are classified properly. The most famous example of the perceptron's inability to solve problems with linearly non-separable vectors is the Boolean exclusive problem. The solution spaces of decision boundaries for all binary functions and learning behaviors are studied in the reference. In the context of neural networks, a perceptron is an artificial neuron using the Heaviside step function as the activation function. The perceptron algorithm is also termed the single-layer perceptron, to distinguish it from a multi-layer perceptron, which is a misnomer for a more complicated neural network. As a linear classifier, the single-layer perceptron is the simplest feed-forward neural network. Learning algorithm: below is an example of a learning algorithm for a perceptron. For multi-layer perceptrons, where a hidden layer exists, more sophisticated algorithms such as backpropagation must be used. Alternatively, methods such as the delta rule can be used if the function is nonlinear and differentiable, although the one below will work as well. When multiple perceptrons are combined in an artificial neural network, each output neuron operates independently of all the others. Thus, learning each output can be considered in isolation. Definitions: we first define some variables, denotes the output from the perceptron for an input vector. Is the bias term, which in the example below we take to be 0. Is the training set of samples, where, is the dimensional input vector. Is the desired output value of the perceptron for that input. We show the values of the features as follows: is the value of the th feature of the th training input vector. To represent the weights, is the th value in the weight vector, to be multiplied by the value of the th input feature. Because, the is effectively a learned bias that we use instead of the bias constant. To show the time dependence of, we use, is the weight at time. Is the learning rate, where. Too high a learning rate makes the perceptron periodically oscillate around the solution unless additional steps are taken. Steps: 1. Initialize the weights in the threshold. Weights may be initialized to 0 or to a small random value. In the example below, we use 0. 2. For each example in our training set, perform the following steps over the input and desired output. 2a. Calculate the actual output. 2b. Update the weights, for all feature. 3. For offline learning, the step 2 may be repeated until the iteration error is less than a user-specified error threshold, or a predetermined number of iterations have been completed. The algorithm updates the weights after steps 2a and 2b. These weights are immediately applied to a pair in the training set, and subsequently updated, rather than waiting until all pairs in the training set have undergone these steps. Convergence: the perceptron is a linear classifier, therefore it will never get to the state with all the input vectors classified correctly if the training set is not linearly separable, that is if the positive examples cannot be separated from the negative examples by a hyperplane. But if the training set is linearly separable, then the perceptron is guaranteed to converge, and there is an upper bound on the number of times the perceptron will adjust its weights during the training. Suppose that the input vectors from the two classes can be separated by a hyperplane with a margin, that is there exists a weight vector, and a bias term such that for all and for all. And also let denote the maximum norm of an input vector. Novikov proved that in this case the perceptron algorithm converges after making updates. The idea of the proof is that the weight vector is always adjusted by a bounded amount in a direction that it has a negative dot product with, and thus can be bounded above by where t is the number of changes to the weight vector. But it can also be bounded below by because if there exists an satisfactory weight vector, then every change makes progress in this direction by a positive amount that depends only on the input vector. The decision boundary of a perceptron is invariant with respect to scaling of the weight vector. That is, a perceptron trained with initial weight vector and learning rate behaves identically to a perceptron trained with initial weight vector and learning rate 1. Thus, since the initial weights become irrelevant with increasing number of iterations, the learning rate does not matter in the case of the perceptron and is usually just set to 1. Variance: the pocket algorithm with ratchet solves the stability problem of perceptron learning by keeping the best solution seen so far in its pocket. The pocket algorithm then returns the solution in the pocket, rather than the last solution. It can be used also for non-separable datasets, where the aim is to find a perceptron with a small number of misclassifications. In separable problems, perceptron training can also aim at finding the largest separating margin between the classes. The so-called perceptron of optimal stability can be determined by means of iterative training and optimization schemes, such as the min-over algorithm or the Adatron. Adatron uses the fact that the corresponding quadratic optimization problem is convex. The perceptron of optimal stability, together with the kernel trick, are the conceptual foundations of the support vector machine. The perceptron further used a pre-processing layer of fixed random weights, with thresholded output units. This enabled the perceptron to classify analog patterns, by projecting them into a binary space. In fact, for a projection space of sufficiently high dimension, patterns can become linearly separable. For example, consider the case of having to classify data into two classes. Here is a small such dataset, consisting of 2 points coming from two Gaussian distributions. A linear classifier can only separate points with a hyperplane, so no linear classifier can classify all the points here perfectly. On the other hand, the data can be projected into a large number of dimensions. In our example, a random matrix was used to project the data linearly to a 1000-dimensional space. Then each resulting data point was transformed through the hyperbolic tangent function. A linear classifier can then separate the data, as shown in the third figure. However, the data may still not be completely separable in this space, in which the perceptron algorithm would not converge. In the example shown, stochastic steepest gradient descent was used to adapt the parameters. Another way to solve nonlinear problems without using multiple layers is to use higher-order networks. In this type of network, each element in the input vector is extended with each pairwise combination of multiplied inputs. This can be extended to an n-order network. It should be kept in mind, however, that the best classifier is not necessarily that which classifies all the training data perfectly. Indeed, if we had the prior constraint that the data come from equivariant Gaussian distributions, the linear separation in the input space is optimal. Other linear classification algorithms include Winnow, support vector machine and logistic regression. Example: a perceptron learns to perform a binary NAND function on inputs and inputs, with input held constant at 1. Threshold, 0.5, bias, 0, learning rate, 0.1, training set, consisting of 4 samples. In the following, the final weights of one iteration become the initial weights of the next. Each cycle over all the samples in the training set is demarcated with heavy lines. This example can be implemented in the following Python code. Multiclass perceptron. Like most other techniques for training linear classifiers, the perceptron generalizes naturally to multiclass classification. Here, the input and the output are drawn from arbitrary sets. A feature representation function maps each possible input-output pair to a finite-dimensional real-valued feature vector. As before, a feature vector is multiplied by a weight vector, but now the resulting score is used to choose among many possible outputs. Learning again iterates over the examples, predicting an output for each, leaving the weights unchanged when the predicted output matches the target, and changing them when it does not. The update becomes. This multiclass formulation reduces to the original perceptron when as a real-valued vector, is chosen from, and. For certain problems, input-output representations and features can be chosen so that can be found efficiently even though is chosen from a very large or even infinite set. In recent years, perceptron training has become popular in the field of natural language processing for such tasks as part of speech tagging and syntactic parsing. References: A. Zerman, M.A. and Braverman, E.M. and Levi-Rosonua. Theoretical Foundations of the Potential Function Method in Pattern Recognition Learning. Automation and Remote Control, 25 821 837, 1964. Rosenblatt, Frank, The Perceptron, A Probabilistic Model for Information Storage and Organization in the Brain, Cornell Aeronautical Laboratory, Psychological Review, v65, No. 6, ppA 386 408 doi, 10.1037 per hour 00425519. Rosenblatt, Frank, Principles of Neurodynamics. Washington, D.C., Spartan Books. Minsky M. Allen Papert Essay 1969. Perceptrons. Cambridge, Massachusetts, MIT Press. Freund, Y. and Shapire, R.E. 1998. Large margin classification using the Perceptron algorithm. In Proceedings of the 11th Annual Conference on Computational Learning Theory. ACM Press. Freund, Y. and Shapire, R.E. 1999. Large margin classification using the Perceptron algorithm. In Machine Learning 37, 3, 277-296, 1999. Gallant, S.I. Perceptron-based learning algorithms. IEEE Transactions on Neural Networks, Volume 1, Number 2, ppA 179/191. Mori, Muyor and Rostamizadeh, Afshin. Perceptron Mistake Bounds AR-Ziv, 1305.0208, 2013. Novikov, A.B. on Convergence Proofs on Perceptrons. Symposium on the Mathematical Theory of Automata, 12, 615-622. Polytechnic Institute of Brooklyn. Widrow, B., Lou, M.A., 30 Years of Adaptive Neural Networks, Perceptron, Madeline, and Backpropagation, Proc. IEEE, Vol 78, No 9, ppA 1415/1442. Collins, M. 2002. Discriminative Training Methods for Hidden Markov Models, Theory and Experiments with the Perceptron Algorithm in Proceedings of the Conference on Empirical Methods in Natural Language Processing. Yin, Hongfeng, Perceptron-Based Algorithms and Analysis, Spectrum Library, Concordia University, Canada. External links: A Perceptron implemented in MATLAB to learn binary NAND function, Chapter 3 Weighted Networks, the Perceptron, and Chapter 4 Perceptron Learning of Neural Networks, a systematic introduction by Raul L. Rojas, explanation of the update rule by Charles Elkin, history of perceptrons, mathematics of perceptrons, Perceptron demoplate and an introduction by examples.